Good day, sir. I'm Carly Cebuano, BSMA. So, we are example of ideal gas or perfect gas. So, problem number one. 3 pounds mass of air are contained at 25 psi and 100 Fahrenheit given that air constant is 53.35 feet pounds force over pounds mass. So, what is the volume of the container? So, since the given is the pressure and the air, then the mass, we have to solve this using the formula of PV equals to mRT. So since the pressure is given, P is pressure equals to 225 psi, we need to convert it into pounds feet squared. So in order to convert that 3,600, we equals to 3,600 pounds per feet squared. Then the temperature have given is 100 Fahrenheit. We need to convert it into Rankine. So T equals to 100 degree Fahrenheit plus 400 Rankine equals to 560 Rankine. So since the mass is given 3 pounds, so mass equals to 3 pound mass. So we need to compute that by using the formula of PVMRT. So 3,600 times volume equals to 3. Value of mass is 3. Then 53.35 is the gas constant of air times 560 Rankine. So in order to get the answer, we need to shift solve. So 3,600 x alpha equals 3, 53.35 times 560. So we can get 24.84 feet. So volume equals to 24.84 feet cube. So that's the final answer of the volume of the container. So proceed to problem number 2. So an air compressor delivered 0.20 meter cube of air at a pressure of 850 kPa and 31 degree into an air reservoir, taking the gas constant of air as 0.287 kilojoule per kilogram point Kelvin. Calculate the mass of air delivered. So since the pressure are given, the volume also, and the gas constant of air, then temperature, it's easy to solve by using the formula of PVMRT. So PV equals to mRT. So since the pressure is given 850 kPa times the volume 0.20 meter cube equals to the mass is missing, so mass times the gas constant of air 0.287 times the temperature given is 31 degrees, so we need to add by 273 in order to convert it into Kelvin. 31 plus 273. Okay, so shift solve. 850 times 0.20 equal x 0.287 times 31 plus 273 is 31 plus 273. So we can get the mass is 1.948, or we can round off it on 1.95 kilogram. So 1.95. So we need to proceed to problem number 3. So an oxygen cylinder of volume is 2.3 feet cube, has a pressure of 2,200 psi and is at 70 Fahrenheit. Determine the mass of oxygen in the cylinder. So since the volume is given 2.3 feet cube, then the temperature 70 Fahrenheit, then also the gas constant is 48.29, the oxygen of. So we need to solve by PV/MRT. PV equals to MRT. So since the pressure equals to 2,200 psi, then we need to add by 14, the constant of 14.7 psi. So 2,200 plus 14.7 equals to 2,214.7 psi. Then the temperature given is 70 Fahrenheit. So temperature equals to 7 Fahrenheit. So we need to add this one 460 plus 460 Rankine in order to get the value of Rankine. So 70 plus 460, so equals to 530 Rankine. Then the ideal gas of oxygen is R equals to 48.291 sa oxygen. Then since the pressure, temperature and ideal gas is given, then the volume also is 2.3 feet cube. Then so we can solve this by the formula of PV/MRT. So the pressure is 2,214.7 psi times the volume 2.3 and the volume of the oxygen times 144 equals to the mass times the ideal gas of the oxygen is 291 times the temperature is 530 Rankine. So we need to shift solve. So 2,214.7 times 2.3 times 144 equals alpha x 48.291 times 530 so 6 so the final answer is 28.65 28.665 or 659 or we can round off it to 28.66 so mass equals to 28.66 pounds. So the final answer 28.600. But this time we need to proceed to problem number 4. So if I have a 21 moles of gas held at a pressure of 78 atm and a temperature of 900 Kelvin, what is the volume of the gas? So since the pressure is given, the temperature and the number of moles, we need to find the volume. So using the formula of PV equals to N number of moles, then universal gas constant times temperature. So in order to get the volume, we need to use this formula by converting this V equals to number of moles universal gas T over pressure. So since the number of moles are given, so V equals to 21 mole. Then the universal gas constant is 0.082 atm 0.8 liters over mole times K. Then 900 Kelvin, so the temperature times 900 Kelvin over the pressure is 78 atm, so 78 atm. Then in order to get the final answer of volume, we need to use the Shepsov. So alpha x alpha equals 21 mole times 0.082 times 900 over 78. So the answer is 19.86 or 19.87 in rounding up. So volume equals to 19.86. So the units is the unit of this, so the cancel the mole, the atm, the Kelvin, so the unit is liter. The volume is 19.86 liters. So proceed to problem number 5. So if I have a 2.4 moles of gas held at temperature of 97 degrees Celsius and in a container with a volume of 45 liters, what is the pressure of the gas? So since the number of moles are given, the temperature and the volume, then the universal gas constant, so we need to solve this one by using the formula of PV equals to number of moles universal gas times temperature. So since the pressure, we need to find the pressure, so we need to convert the formula into P equals to number of moles and universal gas constant and temperature over volume. So since the number of moles are given, pressure equals to 2.4 mole times the universal gas constant 0.0821 atm times liter over mole times Kelvin. So times the temperature. Temperature is 97 degree. We need to convert it into Kelvin. So 97 plus 273. 97 plus 273 equals to 370 times 370 Kelvin over volume. So 45 liters. 45 liters. So we need to shift solve in order to get the pressure of the gas. So alpha x equals 2.4 times 0.0821 times 370 over 45 shifts. So the pressure of the gas is 1.62. So 1.62. So pressure equals to 1.62. So the unit of that, we need to cancel the mole, atm, liters, Kelvin. Oh, sorry, the ATM is the units of the pressure. So 1.62 ATM. Or we can convert it into kilogram. So we can get pressure equals to 164.06 kilogram. That's the final answer. So we need to proceed to problem number 6. If I have 72 liters of gas held at a pressure of 3.4 atm and a temperature of 225 Kelvin, how many moles of gas do I have? So since the volume is given 72 liters, then the pressure 3.4 atm and the temperature is 225 Kelvin. So we need to solve the number of moles using the formula of PV equals to number of moles, universal gas constant, then temperature. So we need to convert the formula in order to get the number of moles. So number of moles equals to universal gas constant, temperature over pressure times volume. So since the universal gas constant is 0.0821, universal gas constant 0.0821 atm liters over mole times Kelvin. So since the temperature is 225 Kelvin given times 225 Kelvin, then over the pressure is 3.4 atm. 3.4 atm. So 3.4 atm. Then the volume is 7.2 liters. 72 liters. 72 liters. Then we need to shift solve in order to get the number of moles. 0.00821 225 over 72 times 3.4. So the number of moles is 0.075. 0.75. So number of moles equals to 7, 5, 4, 6 number of moles. Cancel the ATM, Kelvin, then the liters. So the answer is number of moles is 0.07546 moles. Final answer. The temperature. So here are the problem of temperature. Problem number 1. So using the temperature conversion equation, what is the value in Kelvin of 165 degree Fahrenheit? So we need to convert it into Kelvin. So first we need to convert the Fahrenheit to Kelvin. So Fahrenheit to Kelvin, degree of Kelvin. So degree equals to 5/9 times the value of Fahrenheit equals to 165 Fahrenheit minus 32. So the value of degree equals to 5/9. 5/9 165 5/9 165 minus 32. So the answer is 73.88 or 89. 73.89 degree. So we can easily get the Kelvin. So we need to convert the degree to Kelvin. So Kelvin equals to degree plus 273. So the Kelvin equals to the value of degree 73.89 degrees Celsius plus 273. So the value of Kelvin equals to 73.89 plus 273 equals to 346. So 346.89 Kelvin. So that's the final answer of the problem number 1. So we need to proceed to problem number 2. So the problem number 2, what is the temperature in degrees Celsius of a temperature of 468 degree of Rankine? So we need to convert it into the degree Celsius into the Rankine into degree Celsius. So since the Rankine is given 468, so degree Celsius equals to Rankine minus 491.67 times 5/9. So degree equals to the value of Rankine 468, Rankine minus 491.67 times 5/9. So the value of degree equals to 468 minus 491.67 times 5/9. 5/9. So the final answer is 194. So degree equals to 194.85 degrees Celsius. So that would be the final answer. So let's proceed to problem number 3. So, convert 37 degree to both Fahrenheit degrees and Kelvin. So convert 37 degree to Fahrenheit degrees and Kelvin. Fahrenheit equals to 9/5 degree plus 32. So Fahrenheit equals to 9/5, then the value of degree Celsius equals to 37 plus 32. So Fahrenheit equals to 66.6 plus 32. So the value of Fahrenheit equals to 66.6 plus 32. So 98.6. So Fahrenheit 98.6 degree Fahrenheit. And the final answer is 98.6 Fahrenheit. So we need to proceed to problem number 4. A tank contains of 20 kg of air at 200 kPa gauge and 23 degrees Celsius during the heating process. The temperature of air rises. For safety purposes, technicians installed a relief type valve so that pressure of air inside the tank never exceeds 260 kPa gauge. At what air temperature the relief valve will start releasing air? So since the T1 temperature is given 23 degrees Celsius, and the T1 pressure 1 equals to 200 kPa gauge, 200 kPa. Then P2 pressure 2 equals to 260 kPa, 60 kPa. So the temperature 1 add plus 273 in order to get the temperature of Kelvin. So 273 plus 23, 296 Kelvin. Then the pressure 100 kPa, need to add the constant atmospheric plus 101.325 kPa atmospheric. So equals to 301.325 kPa atmospheric. Then also the P2 plus 101.325 kPa equals to 260 plus 101.325, 61.325 kPa. So since the temperature 2 is unknown, we need to get that by using the formula of PT2 equals to T1 P2 over P1. So T2 equals to value of T1 equals 296K. Then But the value of P2 equals to 361 361.325 kPa over the value of P1 361.325 kPa. Then shift solve. So alpha equals 296 301 301.325 over 361.325 then shift solve. So the answer is 355. So the answer is 261 over 31. So the answer is T2 or T2 equals to 355 Kelvin. So T2 equals to 355 Kelvin. So proceed to problem number 5. So problem number 5. 1 kilogram of water CV constant volume equals to 4.2 kilojoule over kilogram Kelvin is heated by 300 BTU of energy. What is the change in temperature in Kelvin? So formula for that solution is Q equals to mass constant volume temperature. So the value of work done equals to Q equals to 300 BTU times the value of the convert the BTU into kilojoule. So 1 BTU equals to 1.055 kilojoule equals to 300 1.055 over 1. So 316.50 kilojoules. Then the value of Q equals to 316.50 kilojoule equals to times the value of mass 1, then the value of constant volume 4.2 and the temperature. So the answer of temperature equals to 316.50 minus alpha equals 1 times 4.2 alpha x. So the answer is 75.357 or 75.36 Kelvin. So that's the final answer. So next is Charles law. So here's the problem number one of Charles law. So the temperature of 4.82 pound of oxygen occupying 8 feet cube is changed from 110 Fahrenheit to 200 Fahrenheit while pressure remains constant at 115 psi absolute. Determine the final volume. So since the volume is given, so the volume 1 equals to 8 feet cube. Then um, the temperature 110 T1 equals to 110 Fahrenheit. So Fahrenheit in order to change it into Rankine, we need to add plus 460 equals to 570 Rankine. So T2 equals to 200 Fahrenheit. So 200 Fahrenheit plus 460 equals to 660 Rankine. So the missing is the V2, the final volume. So in order to get a sense, we have the volume 1, T1 and T2 and the pressure remains constant. We need to use the formula of V1 equals to T1 equals to V2 over T2. So we need to put the value of V1. So 8 over the T1 is 570 Rankine equals to V2 over the value of T2 equals to 660 Rankine. So we need to solve by using the shape solve. So 8 over 570 equals V2 alpha x over 660. So shape solve, the answer is 9.26 feet. So the value of the final volume equals to 9.26 feet cube. So the final answer is 9.26 feet cube. So next, about the pressure. So problem number 1. If 6 liters of gas at a pressure of 100 kPa are compressed, reversibility according to PV squared equals to C until the volume becomes 2 liters. Find the final pressure. So since the PV squared equals to C, or constant. So P1 V1 squared equals to P2 V squared. So given is the pressure 1 equals to 100 kPa. So 100 kPa, then the V1 equals to 6 liters. So 6 volume 1, 6 squared equals to, then P2 is missing or unknown, then V squared equals to 2 liters, so 2 squared. So find the P2. So pressure 2 or final pressure equals to 100 times 6 squared alpha equal, then alpha x times 2 squared. So shift solve, answer is 900. So the final pressure equals to 900 kPa. Final answer. So proceed to problem number 2. So problem number 2. A closed vessel contains air at a pressure of 140 kPa gauge and a temperature of 20 degree. Find the final gauge pressure if the air is heated at a constant volume of 40 degrees Celsius. Take the atmospheric pressure as 759 mmHg. So, we need to convert the atmospheric pressure into kPa. So, pressure atmospheric equals to the given 759 mmHg times 760 mmHg equals to 101.325 kPa. So the value of atmospheric pressure equals to 759 over 101.325 over 760. So the answer is 101.19. So 101.19 kPa. 0.19 kPa. Then the pressure 1, so since kPa, so pressure 1 equals to 140 plus the pressure 101.325 equals to 101.325 plus 140 equals to 241 101.325 plus 140 equals 241.325. That's why temperature 1 equals to 20 degree plus need to add 273 in order to get the units of Kelvin. 273 equals to 293 Kelvin. Then the temperature 2 equals to 40. The value of temperature 2 is 40 degree. Add also 273 equals to 40 plus 273, 13 Kelvin. So that need to use the formula of P1 equals to T1 equals to P2 over T2. So pressure 1 equals to 214.325 kPa over the temperature is 293, temperature 1, then pressure 2 over temperature 2, 313 Kelvin. So P2 equals to 214.325 over 293 equals, so after x over 313. So the answer is P2 is 228. 214.322 313 241, I mean 241
41. So shift solve. The answer is 257. 257.80 kPa gauge. So the final answer is 257.80 kPa. Since the temperature one is converted into Kelvin, so we need to convert also the temperature too. So the temperature 2 is 60 degree. So 60 degree plus 273 equals to 60 plus 273 333. So 333 Kelvin. Then we need to use the formula of P1 over T1 equals to P2 over T2. So the P2 again is unknown. Then P1 is 261. P1 equals to 261.20 over temperature 1 is 303 equals to P2 over 333 Kelvin. Then the pressure 2 equals to 261 over 303 alpha equal P2 alpha x over 333 shift solve equals to 286. The final answer of P2 equals to 286 or 287 kPa, right? Minus the P gauge or the atmospheric pressure of 261.20. I mean the pressure ATM, the atmospheric pressure 101.20. So minus so P2 equals to 287 minus 101.20. So P2 equals to 287 minus 101.20. So the answer is 185.8. So 185.8 kPa. So that's the final answer of pressure. So let's proceed to problem number 4. An automobile tire is inflated to 32 psi pressure at 50 Fahrenheit. After being driven, the temperature raised to 75 Fahrenheit. Determine the final gauge pressure assuming the volume remains constant. So given pressure 1 equals to 32 psi gauge, then temperature 1 T1 equals to 50 Fahrenheit plus 160 to get the value of Rankine plus 510 Rankine T2 equals to 75 Fahrenheit plus 460, so equals to 75 plus 460, 75 plus 460, 535 Rankine. Then we need to get the value of P2 or pressure, final gauge pressure. So formula P1 over T1 equals to P2 over T2. Then equating the formula into P2 equals to P1 T2 over T1. So to use the formula P2 equals to the value of P1 32 PSI gauge plus the constant of PSI 14.696 PSI times the value of the temperature to 535 Brandken. So over T1 510 Brandken. So P2 equals to 32 x equals 32 plus 14.696 times 535 235 over 510. So, so the answer is 48.9850 48.9850. So since we add the constant of PSI is 14.696 into converting to gauge pressure. So converting to gauge pressure. So P2 equals to 48.9850 minus 14.696. So P2 equals to 48.9850 minus 14.696. So the answer is 34.289 or 34.29. 34.29 is I gauge. So the final answer is 34.29 is I gauge. Then proceed to problem number 5. So problem number 5. What is the resulting pressure when 1 pound air at 15 psi atmospheric 200 Fahrenheit is heated at a constant volume to 800 Fahrenheit? So going to get the answer, we need to use the formula of P1 over T1. So P1 over T1 over T1 P2 over T2. Since the given is P1 equals to 15 psia, temperature 1 equals to 200 Fahrenheit. Plus 460 in order to get the temperature of Rankine. So 460 to 660 Rankine. Then is heated to temperature 2 equals to 800 Fahrenheit plus 460 equals to 1260 Rankine. So by using the formula P1 value of P1 equals to 15 psi over the value of T1 660 mankind equals to P2 over the value of T2 1260 mankind. So cancel. P2 equals to 15 over 660 alpha equal alpha x over 1260. So the final answer is 28.636 or 28.64 the final answer in pressure P2 equals to 28.64.
So here the example of Boyle's law. Problem number 1. The temperature of an ideal gas remains constant while the absolute pressure changes from 103.4 kPa absolute to 887.2 kPa absolute. If the initial volume is 80 liters, what is the final volume? So since the pressure pressure 1 is given 103.4, then the pressure 2 is 827.2 kPa, then the volume 1 is 80 liters. We need to find the volume 2. Hence the temperature remains constant. So we need to use the formula of P1 V1 equals to P2 V2. So since the pressure 1 is given 103.4 kPa, 103.4 kPa times the volume is given, the volume 1 is 80 liters times 80 liters equals to the pressure 2, 827.2 kPa. So 827.2 kPa times the volume 2. So in order to get that, we need to use the shift zone. So 103.4 times 80 equals times 827.2 times x. So shift zone. So the volume of the final volume is 10. The final volume. So V2 equals to 10 liters. The final answer of problem number 1. Then we need to proceed to problem number 2. So 3 cubic meter of air at a pressure of 20 kPa gauge is compressed at a constant temperature to a pressure as 425 kPa gauge. Calculate the final volume of the air. So since the pressure also is given 20 kPa gauge, so we need to add, and the constant of air is 101.325 kPa. So pressure 1 equals to 20 kPa plus the atmospheric pressure is 101.325 kPa. So 20 plus 101.325 kPa equals to 121.325 kPa. Then the pressure 2 is 425 kPa gauge, so equals to 425 kPa plus the atmospheric pressure 101.325 kPa equals to 25 plus 101.325 526 26.325 kPa. Then the volume is given is volume 1 equals to 3 meter cube. So 3 meter cube. 3 meter cube. So since the P1 and P2, then volume 1 is given, we need to calculate the volume 2 using the P1 V1 equals to P2 V2. So since we need to use the shift solve. So 121.325 times 3, the volume 1 equals to 526.325, the P2 times V2. So now we are going to shift solve. So 121.325 times 3 equals times 526.325 times so the final answer of the volume is 0.69. So 0.69 meter cube. So V2 equals to 0.69 meter cube. Then so we need to proceed this time we need to proceed to the problem number 3. Since the problem is assuming compression is according to the law PV equals to constant, calculate the initial volume of gas at a pressure of 2 bar which will occupy a volume of 6 meter cube when it is compressed to a pressure of 42 bar. So since the P1 is given and the P2 and V2, we need to find the volume, the initial volume. So since the P1 is given 2, then the P2 is 42 bar and the V2 is 6 meter cube. So we need to use the formula of P1 V1. P1 V1 equals to P2 V2. So we need to put the equivalent of each pressure and the volume. So the pressure 1 equals to 2, then we need to find the V1 equals to 42 bar is the value of pressure 2, then the volume 2 is 6 meter cube. So we need to solve this one by shift solve. So 2 alpha x alpha equal 42 times 6 shift solve. So the value of x equals to 126 meter cube. So V1 equals to 126 meter cube. The final answer. So that's it about the Boyle's law. Thank you.